So we've spent the whole last chapter figuring out, how do I take the derivative of this type of function or that type of function? It's a lot of the power rule and the chain rule, for the most part, is kind of what we're using. Some nice properties that say I could split up a derivative over addition and subtraction, and I can't do that with multiplication or division, but then I have these other kind of formulas I can use. So what we're going to do now is take a look at some ways we could apply the derivative in certain contexts. This first one, it might be a bit of a stretch to call it an application. It's not like we're solving like a lot of actual problems here, but we are applying the concepts to another scenario. So we're just going to look at tangent and normal lines. And tangent lines, that was the basis, sort of the foundation of us developing what the derivative was. This whole notion of what is a derivative was so that we could figure out what's the slope of a tangent line. And we'd say, can I find the slope of a line tangent to a curve at some point, right? And we knew that meant that we're going to find the derivative and then evaluate it at that point. And here, we're just going to go a little further and say, maybe I don't just want the slope. Maybe I want the equation of the whole line. And in that case, if I know the point and I know a slope, I can get an equation of a line, right? It's the same line algebra that you've done since probably one of the first times you ever took an algebra course. And then we'll move on also to include normal lines. And a line is normal to a curve if it's perpendicular to the tangent line. So we use words like we use the word perpendicular to compare two lines. We use normal if I'm comparing a line to a curve. So it's kind of like thinking about it being perpendicular to the curve, but we usually reserve the word perpendicular to refer to two lines. So let's start with an example. Let's say I want the equation of the line tangent to the parabola y equals x squared minus 1 at the point negative 2, 3. Now, they've told us a point, right? And I just need a slope and a point to get the equation of a line. So I'm going to use calculus to help me get the slope. So if y is equal to x squared minus 1, I'm going to find the derivative of y with respect to x, dy dx. That'll give me the tangent slope. And we just get 2x. And so the tangent slope is what I get when I evaluate this at the point they gave me. So, and I only need to know the x-coordinate of the point, in this case, to find that slope. So 2 times negative 2, or negative 4. So there's our tangent slope. And now we'll put together the equation of a line. And when I'm putting together the equation of a line, I almost always default to using the point-slope form. I find it easiest. So y minus y1 is equal to m times x minus x1. And I know my x1, y1, that's the point they gave me. So this is y minus 3 is equal to negative 4 times x plus 2. And, unless it's specified, you could leave the equation of a line in point-slope form. A lot of people default to getting it in slope-intercept form, and that just takes a little bit more algebra. So I'm going to take just a moment here, and let's just sort of see, when we're doing a problem like this, we should be able to kind of see very visually that our result is correct. If I plot the graph of x squared minus 1, and then on top of that I'll plot the graph of our line negative 4x minus 5. Let me set the window. Oh, that looks pretty good. Minus 5 to 5 on both axes. Let's see what it looks like. So there's the parabola, and there we go. So there's the line negative 2, 3, or the point negative 2, 3 right here, and that tangent slope definitely looks, or that line definitely looks tangent. Maybe I'll zoom out a little bit. Yeah. Yeah.
Your equation in the notes is plus 5.
Oh. Well, that's silly. -8 plus 3 is -5, right? Yeah, okay. Want to do another one? Hearing an overwhelming positive response to that question, we'll go ahead and do another one. All right, so here we're going to find the equation that's normal to this ellipse they gave us, and then they gave us this point. And so we have this nice figure. Here's the ellipse. Here's the point at the point 1, 2. And so when we say normal, right, this means it's perpendicular to the tangent line. So, you know, that certainly seems like that's the line that we're looking for. That's what we mean when we say that it's normal. Now, this problem is really similar to the last one. I mean, obviously we had the equation that they've given us is an implicit function, so we're going to have to use implicit differentiation to find dy dx. But it's similar in that they gave me the point and I have to use calculus to get the slope. So let's begin that process. What should I do to start out, or who wants to get us started finding dy dx? Yes.
8x plus
18y dy dx. Good. Yeah, good. So this means, you know, we could throw the 8x on the other side. This means that 18y dy dx is equal to -8x. And then to find dy dx, all we need to do now is divide by 18y. If we reduce, we get -4x over 9y. So what I'm going to do now, right, that's dy dx. Notice that we need both coordinates to get the slope, but that kind of makes sense, right? If I knew only the x coordinate, like if I knew x was 1, I wouldn't know if I was talking about this point or this point, and they definitely have different slopes, right? So I need both coordinates to find the slope of the tangent line. And once I get the slope of the tangent line, what I want is a normal line, I'm just going to take its opposite reciprocal, and that's the slope that we're going to use. So let's evaluate. Evaluate the derivative at the point 1, 2, and that's -4 times 1 over 9 times 2, and that's twice -2/9. So that's m tan, and what we want is the normal slope. Now usually, so here's a little bit of new notation. We write m tan for the tangent slope. For the normal slope, I usually write m and then a little subscript. It's like an upside down t. It just is a symbol that means perpendicular in geometry. So that normal slope is +9/2, opposite and reciprocal. So we found the slope. They gave us the point, and that means we're pretty much ready to get the equation of the line. So I start with my point slope formula. Y minus 2 is equal to 9/2 x minus 1. You could leave it in this form, or we could get it in slope-intercept form. If we add 2, then we get 9/2 x minus 9/2 plus 4/2 is minus 5/2. And you could write it in either form. Questions about that example? So those first two examples were kind of similar. They gave us a point, right? They gave us the curve. They pretty much always tell you what curve we're talking about. They gave us the point, and then they just said the line we're looking for is either going to be tangent at that point or normal at that point. We use calculus to get that slope. The next one's a little bit different. This asks us to find the equational line that has a slope of 4 and is normal to the curve y equals 1/2 x to the 4th plus 1. So what's different? What do you notice?
We have the slope.
They gave us the slope. Yep. What didn't they give us? The point. We're going to use calculus to help us find the point. If they gave us the slope, that means that we know the value or can figure out what the value of the derivative is that we're looking for. And so we're going to use, we're going to find the derivative of the function. We're going to find dy dx as a function and then set up an equation to help us figure out what that point is. So it has a slope of 4 and is normal. So with that information, if it's normal, they're telling us that the normal slope is 4. What does that tell us about dy dx? If it were a tangent slope, I would agree with you. Yeah, negative 1/4, right? Opposite reciprocal. They're saying that when I find mtan, or if I evaluate dy dx at this point, and then take its opposite reciprocal, I'll get 4. So I'm going to just sort of reverse that process. So I want to figure out where is dy dx equal to negative 1/4. So let's begin that process. What is dy dx equal to? Mm-hmm. And then the 1 just goes to 0, right? So that's our derivative. We could simplify, call that 2x cubed. So since dy dx is equal to negative 1/4, that allows us to set up this equation. This equation isn't always true. We're looking for a particular value of x that happens to make this true, right? That'll help us hunt down that point on the curve that we're interested in. I guess algebraically, we could divide both sides by 2, and that'll at least isolate the x cubed. Divide by 2 or multiply by 1/2. So we get x cubed is negative 1/8. So what is x? What's the cube root of negative 1/8? Negative 1/2, yep. So we have the x coordinate. Whatever this point is, we have the x coordinate. How do I get the y coordinate? To what? Which equation? The original one. Yeah, so that's a really important distinction here. We need a y coordinate, not a y prime coordinate or dy dx coordinate. So we need to make sure that if what we want is a y coordinate, we plug it into the y equation. So let's go ahead and do that. So it was 1/2 x to the 4th plus 1. So 1/2 negative 1/2 to the 4th plus 1. Negative 1/2 to the 4th is positive 1/16. If you multiply that by 1/2, you get 1 over 32. Plus 1, or 32 over 32, is 33 over 32. So our point is negative 1/2, positive 33 over 32. What's left to do? Yeah, We want the equation of the line. We have a point, we have a slope. So we're ready to kind of just set this up. Again, I'm going to use the point slope form. The slope, what's our slope? 4, yeah, they gave that one to us. And then x plus a half. We could leave it in this form, or we could get it in slope-intercept form. Let's see, 2 is 64 over 32, and 64 plus 33 is 97. How's that? So the exercises you'll see, which are in a handout, by the way, so don't leave without letting me hand that out to you, will come in a couple of varieties sometimes. So they'll ask you to find the equation of a line, either tangent or normal. They'll give you the curve. And they'll either give you the point, so you need to use calculus to get the slope, like we did in the first two examples, or they'll tell you what the slope is, and you have to use calculus to help you find what that point is.
Okay, so I'm still a little confused as to the difference between a line, a normal line, and a tangent line.
Okay, yeah, so if we look at this curve here, like the previous, they gave us this point, 1, 2. This is the tangent line. This is the normal line. It's perpendicular to the tangent line.
Yes, cool.
Yep.
Okay, thank you.
Other questions?